All right, everybody, we are on chapter 5. This is the last bit that we will do in this course. We're not going to do the whole chapter. We're going to focus on the natural log, e to the x, a to the x, log base, 10, 12, 80, whatever. We're going to do derivatives and integration in this chapter. So before we start, we need to do a bit of a review of log or natural log properties. The natural log is the most common log used in calculus because it has nice, neat properties, as you'll see, for doing derivatives, etc. But logarithmic properties are all kind of standard. So just a quick review of Math 12. Natural log of 1 or log of 1, any logging the number 1 always gives you, hopefully you remember, 0. If you're logging 2 numbers or functions that are being multiplied together, that is the same as adding the logs of each of those individual functions. Natural log of a plus natural log of b. Natural log of a to the power of n. You can drop the exponent down in front, which makes your life a lot easier when you're doing derivatives or integration. So we get n natural log of a. And the last one, if you're dividing, that is the same as subtracting. Okay. So I'll do a couple of examples, give you some practice questions, and then we'll get into the calculus. So the first example, if I say we have the natural log, excuse me, root of 3x plus 2, how can I write that? Well, as you guys know, the square root means to the power of a half. The log rule here, so I can drop that in front. And as you'll see in this lesson, this is a very easy derivative to do as compared to something like that. So logs actually help you simplify derivatives. I know, it seems strange, especially if you have something that looks like this. So x squared plus 3 all squared over x cubed root x plus 1. So this gong show. Well, let's break it up. Simplify it. First of all, I am dividing, so I can subtract. So I get natural log x squared plus 3 all squared minus the natural log of x cubed root x plus 1. And this first bit, this 2 will come down, so that becomes 2 natural log x squared plus 3. Can't really do anything else with that, so I just leave it. These two are being multiplied. Put these brackets in because that means I'm adding these. And instead of writing the square root, we don't like square roots when we're dealing with logs. We want exponents. Why do we want exponents? Because they fall down in front. So then this whole thing becomes 2 natural log x squared plus 3 minus 3 natural log of x minus, because that negative goes to there, 1/2 natural log of x plus 1. And that's about all you can do with that for simplifying. And then normally we would do the derivative. Okay. Before we go on, because we're going to use all of those rules to do these, I strongly suggest you do page 325, numbers 17 to 33 odd. And when you've done that, come on back and we'll see you here. All right. Okay. Hopefully that went okay with you, for you. Now we're going to look at the natural log function. And in one of the previous lessons, I talked about what the natural log function was. We're doing the second fundamental theorem of calculus. I told you that the natural log function is actually the value of the integral, or the area under the graph, of 1t, and x has to be greater than 0. So really, as a quick review, when you're dealing with the natural log, here's the 1 over x, or 1 over t. 1. I'll just mark x there. So when you're actually doing the natural log, you're finding this area in here. That area is the natural log of x. Okay. Hopefully you remember from Math 12 the natural log graph. It's a log graph. Can't log a negative number like this. It has a domain of 0 to infinity. Can't log negative numbers. It has a range from negative infinity to positive infinity. It is continuous. And it is concave down. All right. So based on this definition, we can figure this out using second fundamental theorem of calculus. So if I said the derivative with respect to x of the natural log of x, well, what that means is the derivative with respect to x of the integral from 1 to x of 1 over t dt, which hopefully you remember from the second fundamental theorem, the x just goes in for t is 1 over x. And that is the derivative of the natural log of x. It's super straightforward. Now, obviously, we don't usually have x. We usually have something more complicated in there, but that's fine. We can use chain rule. So if I said, this is one that's on your formula sheet, the derivative with respect to x, of the natural log of u is some function of x. It's 1 over u, which is this bit, times whatever the derivative of u is, u primed. So the shorthand is it's just u primed over u. All right. If you remember those two formulas, really just remember the second one here. You can do every single one. Because this one, if we're dealing with x, the derivative of x is just 1, so it's 1 over x. There you go. All right, we're going to do a bunch of examples, and then I'm going to send you on your way. So, number 1, I want to know the derivative of the natural log of 2x. Well, if that's my u, it's 1 over 2x times the derivative of 2x, u prime. What's the derivative of 2x? It is 2. The 2 cancel, and I'm left with 1 over x. All right, that's it. A bit more complicated one. The derivative of the natural log x squared plus 1. Well, it's u prime over u. So first thing you do is put whatever u is. By the way, that is u. So I just go x squared plus 1, and then I multiply it, or put on top the derivative of that function. What's the derivative of x squared plus 1? 2x. And that's it. Number 3. The derivative of x natural log of x. Okay. So hopefully you recognize this is going to be a, oh my gosh, not quotient, but product rule. Wow, sorry, that took me so long because it's two functions being multiplied together. It's x and it's natural log of x. Okay, so product rule, you don't remember, look it up, says derivative of, what's the derivative of x? Is 1 times the second function plus the derivative of the second function, which is 1 over x times the first function, which is x. So this just becomes natural log of x plus these x's cancel, and I get 1. Natural log of x plus 1. Number 4. The derivative of the natural log of x all cubed. So this is the same as writing the derivative like that, although you don't see it that often. It's the same thing. The 3 on the natural log. So this is a chain rule problem. 3 falls down. Natural log of x squared times the inside derivative. What's the derivative of natural log of x? It is 1 over x. Alright, so this shortens to 3 natural log squared of x over x. And those x's don't cancel because this x here is inside the natural log. It's the same as writing this. You cannot cancel those x's. You just leave it and walk away. Now, how is that different than this? The derivative of the natural log of x cubed. Well, you have a couple ways to do this one. The first way is go, alright, it's 1 over x cubed times the derivative of x cubed, because this one has the cube on the x, which is 3x squared. And then if you, those would cancel, two of those, and you're left with 3 over x. That's one way to do it. The other way to do it is to, remember your log rules, drop the 3 down. This is the same as the derivative of 3 natural log of x. And a constant, just pull out. Derivative of the natural log of x is 1 over x times the 3, which is 3 over x. Same thing. I prefer the second way, but I don't really care. And you don't have to show all the steps. You could do them in your head. Number 6. All right. So if f of x is equal to the natural log of root x plus 1, what is the derivative? Find f primed. Well, we don't like square roots when we're dealing with logs. So I rewrite it, x plus 1 to the power of 1/2, and drop the 1/2 down. This is much easier to derive because the constants you don't have to worry about. You forget about them like I did. You can pull them out. So f is going to be the 1/2 that stays there. The derivative of this is 1 over x plus 1 times the derivative of x plus 1, which is just 1. This becomes 1 over 2 times x plus 1. And that's it. All right. Last one before I give you some questions. 7. We have f of x is equal to natural log of x squared plus 1 whole squared over root 2 of x cubed minus 1. Now, if you were going to do this without simplifying it, you've got a product rule on top and you've got a quotient rule with the denominator. Plus you got a chain rule in here with this 2. That is going to be an absolute gong show to do. So we use the log rules to make our life easier. We are dividing, so this is equivalent to this. And I'm going to get rid of that square root and write it to the power of 1/2. And these 2 are being multiplied. I'll break them up. going to drop the 1/2 down. And then the derivative, I'm going to drop this 2 down there. There we go. Okay, now, so we've simplified it. Now I can do the derivative. So, 1 over x. Second one, 2, because it's constant, we don't care. 1 over x squared plus 1 times the derivative of that, which is 2x, minus, I'll simplify after. 1/2 is a constant, so we leave them there. 1 over 2x cubed minus 1 times the derivative of that, which is 6x squared. So to simplify it, plus into 4x over x squared plus 1 minus this 2 here and this 6 will simplify to a 3. And so I'll get 3x squared over 2x cubed minus 1. And that is it. Then you can combine them and make common denominators. I'd be happy if you left it right there. Okay, page 325, numbers 41 to 59 odd, and number 73. I strongly encourage you to practice these. They are straightforward if you do them all the time. Okay, there's one tiny little section left that I want to do. So come on back when you are done. Okay, hopefully that went okay. There's one more question where I want to show you the power of logs. And that is when the function does not have a log. So we have y is equal to x minus 2 all squared over x cubed root x squared plus 1. Now if I asked you for y primed, said find y prime or dy dx, you would curse me because we have a chain rule up top, we have a quotient rule, and a product rule on the bottom. So there's 3 different things going on there. It's going to get super ugly, and to simplify, it's going to be a gong show. But what you can actually do to make your life easier, as you saw here, when you have a log of a bunch of junk, you can use that log to simplify it. Well, I can do that here, even though there's no log there. What I do is I introduce one by logging each side. Okay? Just because what you do on one side, you have to do the other, just like when you learn that in who knows what grade. So I've logged both sides. Now I'm going to simplify the right side. Whoops. Sorry. So the right side will become, now I'm going to do this quickly. We're dividing, so the top part minus all the bottom part, but I'm going to drop the exponent down. So I'm going to get 2 natural log of x minus 2 minus, I always bracket when there's 2 things in the bottom because they're actually a product rule. And I'm going to do this quickly. 3 natural log of x, so that 3 fell down, minus, that's a 1/2 power, natural log of x squared plus 1. Okay? I just did a bunch of stuff in one step, right? And this subtraction sign is because these are being divided. And then this, that should be a plus, sorry. That should be a plus because these are being multiplied. And then I drop their exponents down all at once. I can clean that up a little bit. I can write it as 2 natural log of x minus 2 minus 3 natural log of x minus 1/2 natural log x squared plus 1. And it's the natural log of y is equal to all that. Okay, now I do the derivative. So the derivative, you have to do both sides. It's sort of like implicit. But the derivative of natural log of y is just u primed over u. So in this case, it's going to be y primed over y is equal to you do each of these derivatives. 2 over x minus 2, the derivative of x minus 2 is 1, so that's that part. Minus 3 over x, that. Minus 1/2 over times x squared plus 1, the derivative of that is 2x. Those 2's are going to cancel. So I'm going to end up with y prime over y is equal to 2 minus 2 minus 3 over x minus x over x squared plus 1. All right, now we're not done yet because we're trying to find y primed. I don't have y primed, I have y primed over y. So I'm multiplying the y up. I get this. That still doesn't look right because we've got this stupid y here. But what was y equal to? It was equal to that. So the actual derivative is x minus 2 all squared over x cubed x squared plus 1 to the power of a half. That's y times all this stuff. I'm going to run out of room. 2 over 1 minus x, or x minus 2. 3 over x minus x over x squared plus 1. And there you go. All right? That's y the original times all this. All right? And this whole thing is y prime. It is the derivative of that original function. Super complex. It looks ugly. But if you had to do that with product, chain, and quotient rule all at once, that would be a lot uglier. Okay. There's one more thing I wanted to show you. So, hang on. I don't want that. What I want is this. Okay. The final thing is I just want to show you what happens if you have an absolute value in your log. Because logs are only work for positive numbers. You only log a positive number. So often, let's title this natural logs absolute values. Okay. Well, if I'm asking you for the derivative of the natural log of the absolute value of u. The absolute value of u will equal u if u is greater than 0. If I agree with that, so if I have 1 in there, I get 1. That's what that's saying essentially. So that means that natural log, the derivative of the natural log of u would be u primed over u. Because if that's an absolute value, we're saying it's equal to u if u is positive. No change. The absolute value of u is equal to negative u if u is less than 0. In other words, if I put negative 1 in here, that's the same as negative of negative 1, which gives me positive 1. Okay? So that means I'm doing the derivative of the natural log of negative u. Well, that is over negative u, 1 over that, times u primed. And there's a negative there, so it's negative u primed. What happens to the negatives? They disappear, so I get u primed over u. It's the exact same thing. So if there's an absolute value, it's still equal to u primed over u. And the example they use in the book is, if I say f of x is equal to the natural log, the absolute value of cos x, well, that's my u. So I know it's going to be u primed over u. So it's over cos x. What's the derivative of cosine? negative sine of x. Sine x over cos x is tan x. There's a negative there, so it's equal to negative tan x. And that is the derivative of natural log absolute value of cos x. Okay? So it doesn't matter if there's an absolute value. It is still u prime over u. I did not assign any questions. Page 326. 89, 91, and 92. Best of luck. Let me know if you have any questions.